Hey guys, welcome to Safi Mixed. In this video, I'll talk about the procedure of finding the direction of a three-dimensional vector. We know how to find the direction of a plane vector or of a two-dimensional vectors through its components. That is, the direction of a vector in the xy plane is given by theta equals or tangent theta, the ratio of the y component to the x component. That is, we take the ratio of the two components in the argument of tangent inverse, where a sub y obviously represents the y component and a sub x represents the x component of the vector. However, we don't have such a simplified equation for finding the direction of three-dimensional vectors. So let's begin. How can we find the direction of a three-dimensional vector? That is, suppose we have a vector A which can be written in the form of a sub x multiplied with unit vector I plus a sub y multiplied with unit vector j and a sub z multiplied with unit vector k, where I, j and k are the unit vectors along the components along the axis of Cartesian coordinate system. Written in this form means that we know about the components of the vectors, that we know about the magnitude of a sub x, a sub y, and a sub z. With that information in hand, we can find a unit vector in the direction of A, which is defined by A hat equals vector A divided by its norm. And using this relation, we can write the unit vector as ax divided by the norm of A times unit vector I plus a sub y divided by the norm of A unit vector j plus a sub z divided by the norm of vector A times unit vector k. So I call this equation 1. Equation 1 is in fact a unit vector in the direction of vector A. One can easily specify that this is unit vector by finding the magnitude of A hat, where the norm of a vector is obviously we know is given by the square root of the sum of the square of the components, that is ax squared plus ay squared plus a sub z squared. Since we know about the components of vector A, therefore we can find its magnitude and can construct the equation for unit vector. I want to rewrite this equation into a more simplified form, that is the unit vector A I'm writing in the form of a sub x hat times unit vector I plus a sub y hat multiplied unit vector j plus a sub z hat multiplied with unit vector k. So I represent equation 1. So I just rewrite equation 1 into this form and call this equation 2. From equation 2, we want to find the angles of the unit vector A along x, y, and z axis. And that I can easily do by taking the dot product of unit vector I, unit vector j, and unit vector k one by one with unit vector A. That is, if I take the dot product of unit vector I with unit vector A, I can write I dot A equals the magnitude of unit vector I times the magnitude of unit vector A times the cos of the angle between these two vectors. And I'm writing the angle between I and unit vector A as alpha. Now the magnitude of unit vector I and unit vector A are equals 1, so the product of these is also 1. I can write the right side of equation just equal to cos of alpha. Remember, alpha is the angle between unit vector I and A. That is, alpha is the angle that unit vector A is making along the x-axis of the Cartesian coordinate. And from equation 2, using the orthogonality condition on unit vectors, that is I dot I equals 1, I dot j equals 0 equals I dot k, I can straight away write I dot A equals A sub x hat, and we know A sub x hat equals A sub x divided by the norm of vector A. And I call this equation 4. So I can write comparing equation. So comparing equation 3 and 4, I can write cos alpha equals a sub x divided by the norm of vector A. And from this I can straight away find the angle alpha. That is, I can find angle alpha equals arc cos in the argument a sub x divided by norm of vector A, where I'm writing arc cos for cos inverse. So equation 5 defines the angle of the unit vector A, r of the vector A, along x-axis of the Cartesian coordinate. I repeat the same procedure for the other components. That is, I project the unit vector A along y-axis, and that I can do by taking the scalar product of j with unit vector A. And if I do that, I can write j dot A equals a sub y hat equals cos beta, means I'm taking the angle along y-axis made by the unit vector A equals beta. And from this I can straight away construct beta equals arc cos, and in the argument ay divided by the norm of vector A. So we define the angle along y-axis of the unit vector A, r of vector A, is known to us as well. That is, now again projecting unit vector A in the direction of z-axis, that is taking the dot product of unit vector k with unit vector A, I can write k dot A equals a sub z hat equals cos of gamma. That means the angle of the unit vector A along z-axis I'm representing with gamma, and from this I can straight away write gamma equals arc cos a sub z divided by the norm of vector A. Using values from equation 5, 6, and 7, we can write the unit vector in terms of the angles alpha, beta, and gamma in the form unit vector A equals cos alpha times unit vector I plus cos beta times unit vector j plus cos gamma times unit vector k. The cosines of the angles alpha, beta, and gamma are called direction of cosines. These angles completely specify the direction of the 3D vector in terms of the components and the norm of the given vector. If I draw the vector on a Cartesian coordinate, it will look like this. That is, I'm taking z-axis along the vertical, that direction like y-axis, and perpendicular to the wall is x-axis, and that is the direction of the vector. And obviously unit vector points in the direction of vector A. So I'm writing the angles as alpha, beta, and gamma, and knowing the angle alpha, beta, and gamma, we can exactly know the direction of the vector. So the direction of a 3D vector cannot be described in terms of a single vector like in the case of two-dimensional vector. Rather, the direction of a 3D vector is described in terms of direction cosines. And the direction cosines are exactly expressible in terms of the ratio of the components of the vector to the norm of the vector. At the end, I would like to remind you, please don't forget to hit the like button on the video and to subscribe to Safi Next. Thanks for watching.